So, good afternoon, everyone. This session is about the new in-memory OLTP feature in SQL Server 2014. Show of hands if you saw the SQL Server Foundational session this morning. Yeah, fair number of you did. So you saw the demo of in-memory OLTP, and you saw this amazing 27x performance improvement just by migrating a table and some stored procedures. Now, what I want to do in this session is give you an overview of the technology that made this possible, and also inject a little bit of realism in it, in that not every application will have the same kind of performance gain. It depends on a number of factors, which I will also go into to some extent. My name is Jos de Bruin. I'm a program manager with the SQL Server product team, and I work on the project Hackathon, which is the project that is delivering the feature in-memory OLTP. And in fact, the branding in-memory OLTP is relatively new. So it could be that you have heard before about Hackathon, which was announced November last year. Well, this is what we are calling it now, in-memory OLTP. Now, this feature is not the first feature in SQL Server or delivered by the SQL Server team that takes advantage of plentiful memory in servers nowadays. There are things like the column store indexes, which were included in 2012, for which we are delivering an improved version with an updatable column store in 2014, with things like Power Pivot, App Fabric Cache, Stream Insights. These are all technologies leveraging the large amounts of memory in servers. And then, of course, there is the new feature in-memory OLTP, which is part of SQL Server 2014. So if you download CTP1 today, you get this feature and you can use it. Now, what I want to do in this session today is give an overview of the technology, and I want to use a number of common myths about in-memory databases and about this feature and I want to kind of debunk these myths and along the lines explain what the technology is all about and what you can do with it. So things like, this is a recent response to competitors' offerings. This is like DBCC pin tables, an old feature that used to be in the server. So I will go through these myths one by one and explain what the reality is for in-memory OLTP in SQL Server. So, for myth number one, SQL Server in-memory OLTP is a recent response to competitors' offerings. There has been a hype recently, but several of our competitors have been pushing their products, and you may think that, well, this feature is just a response to what these competitors have been doing. The reality is the project started about 4 years ago. Project Hackathon is what it was called. As you can see, this nice little patent cube was awarded for the algorithm with which we implement serializable isolation in a concurrent fashion. And the reason why we started it the reason we started it was to respond to a number of trends we were seeing both from the marketplace as well as in hardware, things with CPU and memory. So if we look at the business trends that we wanted to address, is that when you look at the OLTP space, there is an ever higher demand for higher throughput and lower latency, so ever higher performance. You want to process a lot of credit card transactions at the same time. You want to place your bets as quickly as possible, get these stock trades done very fast. And of course, you want to have a low total cost of ownership. These are the key business trends we want to address. And then there are the hardware trends. So this slide shows you on the left-hand side a graph that plots CPU trends, the right-hand side that plots the cost of memory. So if we first look at the CPUs, the top line, the green line, shows that overall compute capacity is ever increasing. We're still following Moore's law. We still get more and more transistors on the same CPU. However, we also see that actually the clock rates of the cores that you have are stalling. They are holding steady between 2 and 3 gigahertz typically. So what is happening is that each CPU now has multiple cores. It is pretty common for mid-range servers to have CPUs with 8 cores, which means you get a lot of parallelism in the system, which you need to deal with. So a lot of potential contention. And in the meantime, the price of memory is dropping. It's dropping exponentially, as you can see here. This exponential graph drop. The price keeps dropping. It is not uncommon for mid-range servers to have 256 or 512 or even up to a terabyte of memory. And I've heard from people who are complaining that their servers don't support more than 3 terabytes of memory. So more and more memory is being used in the servers nowadays. So these are the trends we want to take advantage of with in-memory OLTP. So if I want to summarize briefly what the feature is. So first off, it is a performance feature. It does not give you more functionality, no, it gives you performance for your OLTP workloads. Second, it is optimized for main memory. All the tables that you want to have use in-memory OLTP all need to fit in memory. And our data structures and algorithms are optimized with the assumption that everything is in memory. And of course, it is targeted for OLTP scenarios, so short-running transactions, relatively simple queries, integrated into SQL Server. So you have one server that has everything. So for example, you can have in your same database, you can have in-memory tables, but also disk-based tables. So we don't, for example, limit the overall size of a database. And architecture for modern hardware trends. So data can fit in memory, and we work with the many cores in the processors by removing contention between concurrent threads. Now, many people think when you say, hey, I have an in-memory feature in SQL Server, many people ask, is this like the old feature DBCC pin table? There's an old feature which we removed from SQL Server a long time ago. But what this feature did was it pinned your table in memory. So all the pages of all the indexes of the table would remain in the buffer pool, would never be phased out. The reality is, it's nothing like that. We already know that if you have some hot tables in your database, some frequently accessed tables in your database, and you have enough memory, these tables will be in the buffer pool anyway. So just putting your tables in memory does not give you a significant gain. Instead, we designed the storage engine from the ground up to benefit from the fact that everything is in memory. So for example, we don't use pages, we don't use a buffer pool. Our atomic unit is the row, and we always address individual rows. We can do that using a memory pointer. We don't need to navigate pages. We don't need to locate a file, locate a page on the file, locate the location in the page. No, we just have a single 8-byte memory pointer to locate the row. So then I want to delve a little bit deeper into kind of the architectural pillars of in-memory OLTP. So at the bottom here, you see the drivers, the main hardware drivers, as well as the main business driver. So we have the decreasing price of memory, stalling CPU clock rates, so individual cores cannot do more work. We cannot expect them to have more cycles available. But we do have many cores on the processors, so we need to deal with a lot of parallelism in the system. And still you want to have a low total cost of ownership. So to the point of memory, it is, as I mentioned, main memory optimized. So our data structures are built in such a way that we can get to the data very quickly in memory. We don't have pages and indexes. This is a very important point. Indexes on memory optimized tables exist only in memory, and they are rebuilt when the server restarts. But apart from that, they exist only in memory, so they're never stored on disk. And we don't have a buffer pool. And because we don't use page-based data structures, we can use stream-based storage. So what we do is we have append-only files to store the durable data. You may wonder, why do we even store this data on disk? Isn't this a main memory feature? Well, we don't want your data to get lost just because the server crashes. So we do persist a copy of your data on disk to maintain the durability of your data on server crash or on failover. But because we have these append-only files, we can optimize for sequential I/O. So you can have even spindles. As long as they have a good sequential I/O, you can use those for your data files. Now, the second point we wanted to address is the stalling CPU clock rate. When you see the CPU clock rate stalls, then the question is, how can you do more with the cycles that you have available? And our answer is, we compile T-SQL stored procedures to machine code. So we take a T-SQL stored procedure, we compile it to a DLL, load it in memory, and then invocation of the stored procedure just becomes a function call into the DLL directly. This greatly optimizes the execution of the stored procedures. Easily 10 to 30-fold increase of performance in the pure execution of the procedure. And then the fact that we have so much parallelism means that in typical traditional SQL Server disk-based tables, you get a lot of contention. Right? Because you have a page-based organization, you have many threads coming in that want to access the same page, and you get a lot of latch contention between these threads. Plus, SQL Server typically uses locking to guarantee consistency between transactions, and this also makes threads wait for each other. With in-memory OLTP, we said we want frictionless scale-up, which means we want just the ability to add processors and scale linearly, which means there cannot be contention between the threads. We don't want threads to wait for each other. So we have a novel transaction mechanism called multi-version optimistic concurrency control. So we use multi-versioning to get rid of the contention between the different threads. And it is optimistic in the sense that we don't want one thread to wait for another. So it will just assume that the other thread will succeed. And if there is a conflict between two transactions, we detect that conflict. And one of the transactions will fail. We'll need to restart. But this gives us a lot of benefits. So, for example, if you don't need to keep track of latches and you don't need to keep track of logs, it means you also don't need a log manager. You don't need the overhead of acquiring the logs, releasing the logs and the latches, and so forth. So this gives us also a lot of benefit in performance. And then, finally, the feature is fully integrated into SQL Server. So the new memory-optimized tables are just T-SQL tables. They're just there in your database. You can just query them. You can manage them using the same tools that you are used to. Management Studio and other tools like SSAS will simply work with the new memory-optimized tables. Plus, you can have in the same database both memory-optimized in-memory tables and traditional disk-based tables. Which means that you are not limited to the size of your memory when you consider the size of your database. So your database can be much larger than your memory, as long as your hot tables fit in memory. And in addition, of course, you get integrated HA, so integration with always-on availability groups, and also things like backup, restore, attach, detach simply work. Okay. So that brings me nicely to the third myth I wanted to address, is that in-memory databases are new separate products. So you may have heard of some of our competitors bringing out in-memory databases, and typically they are a new product. You need to learn a new language, need to learn your new tools, all these things. But we are fully integrated into SQL Server. So I want to explain a little bit deeper what we mean with full integration into SQL Server. So in fact, we integrate fully into the SQL Server engine. This big gray box in the middle represents the SQL Server.exe process. This is the SQL Server engine. This engine takes care of things like the connection handling, you have your parsing, query optimization, query execution, and then on the storage side, these queries are typically executed against the buffer pool, where the pages from tables and indexes are kept in memory. And SQL Server takes care of moving data between disk and the buffer pool. And in the middle, we have the transaction log is depicted. So you have, of course, in your data files, you have the data in your tables. You also have your indexes. And the transaction log contains all the operations on your tables and on your indexes. Now, if we look at in-memory OLTP, memory optimized tables, how they integrate in SQL Server, well, there is a new space in the SQL Server process, in the SQL Server memory, for your memory optimized tables and indexes. And in addition, we have a new type of file group, memory optimized data file group, which is used for the stream-based storage to persist a copy of your data to make sure it's secure when the server crashes. Now, a typical scenario, you would want to move some of your tables in your database from on disk to in memory. So let's assume here I want to move my tables T1 and T2 to in memory. So what you would do is, well, you write a script to drop the original tables, recreate the new ones, and then the situation will look like this. So you have your tables and indexes in memory, and the tables are, a copy of the tables is kept in the memory optimized data file group, and the operations on the tables, rows updated, inserted, deleted, are maintained in the transaction log. Notice no copy of the indexes on disk. Indexes exist only in memory. There's no reason really to keep any of this on disk if the whole table fits in memory anyway. So then we have a feature called query interop, which is used to query the memory optimized tables using the regular T-SQL query execution engine. This integration occurs at a fairly low level, so at the index scan, index seek level. This means that you can practically write any T-SQL query that has both in-memory tables and disk-based tables in the same query, and the execution engine will just take care to compose the results correctly. Then in addition, we have natively compiled stored procedures. These natively compiled stored procedures, they can access only memory optimized tables, but they use native compilation to greatly speed up execution of the queries. So we actually take the query plan from the optimizer. This is compiled to a DLL, to native code, loaded in memory, and then executed. And the execution of these natively compiled stored procedures, from the client point of view, the client doesn't care whether it is a traditional interpreted T-SQL or a natively compiled stored procedure. You have the same connection management, the same TDS protocol that you're using. So you have the same clients, whether you're using ADO.NET SQL client or you're using native client or JDBC even. All these clients will just work with natively compiled stored procedures. And then we have another nifty feature, which we call a non-durable table. Now, non-durable tables are not for everyone, because non-durable tables don't exist on disk. There's no copy persisted in the memory optimized data file group, and operations are not logged in the transaction log. So the data is lost on server crash. However, what you gain here is that transactions do not need to do any I/O. So the log I/O goes out of the critical path for the transactions. There's no I/O whatsoever for transactions on non-durable tables. So if you have transient information or information that is easily recovered, like transient information is, for example, session state for a web server, or ETL data. So if you just want to load data in your data warehouse and you still have your sources, then you can recover your data if the server would crash. So for these cases, you can use these non-durable tables. Okay. Now, that is all really great, and it looks really nice. You can just migrate your tables, and things will just work. You saw in the demo this morning, it looked all very smooth with the migration. I just clicked a button, migrated the table, clicked a button, migrated the stored procedures. Now, it's not always that simple, and in fact, you will always need to do some work at least. You will at least need to enable your database for in-memory OLTP, and you will need to mark your tables as memory optimized. So, if you would recall the demo, and for those who may not have seen it this morning, what I showed here was that we had a baseline here for disk-based table. I migrated a table to in-memory, and then we got this performance gain. Now, this migration step, if you look at the T-SQL code, looks a bit like this. So, to enable your database for in-memory OLTP, you need to at least add the memory optimized data file group. That is a requirement. That's one thing you need to do. And in addition, for your table, I migrated, in this case, I migrated one table. So my original table was a ticket reservation detail. It had one index, which was a primary key, clustered index. So when migrating this to in-memory OLTP, I needed to declare the table as memory optimized, and I needed to use a non-clustered hash index, because clustered indexes are not supported on memory optimized tables. So these were the two things I needed to do for this first step in the migration. For the second step, what I did was I migrated stored procedures, then we got in total, I think what I showed this morning was 26, 27x. In this run, it happened to be 28. It always depends a little bit, because it's always when you're pushing hardware to such bounds, then the behavior sometimes becomes a little bit erratic. As you can see, there are also some spikes here. Now, what I did here, so we see here the jump from this, where I just migrated the table, to this, where I migrated also the stored procedures. Now, to do this, I needed to make a few changes. I changed two stored procedures. One was pretty trivial to change. This one was a little bit more complex. So as an example, I have here the stored procedure on the left, and there happens to be a feature here that is not supported in natively compiled stored procedures. So this feature in this example is querying a system view. That is not supported. Right. So I could not migrate this stored procedure as a whole to natively compiled. So instead, what I did in this case is I pulled out part of the stored procedure. So I pulled out this red section here, this loop, and I moved this to a new natively compiled stored procedure. And you see here the syntax has a native compilation and some other required elements. And then in the original stored procedure, I replaced the T-SQL logic with a call to this stored procedure. So this hopefully gives you a flavor of the kind of changes that are needed if you are going to migrate to in-memory OLTP. It doesn't come for free. And typically, as also the case, the more effort you're willing to put in, the more potential gain you can get. Like, it is often relatively painless to migrate your tables, but if you want to get the full benefits, you want to migrate your stored procedures as well, which is often going to be harder. Okay. Then, the fifth myth I want to address is, well, since my tables are in memory, my data is not durable. It's not going to be highly available. So I will lose it after my server crashes. Well, data in memory optimized tables is fully durable, period. You have the same guarantees as for disk-based tables. The same high availability, including always on. Data is persistent on disk. It will survive server crash. So then the next question that would come to mind is, well, you are persisting this on disk anyway, so you are doing the I/O. So where does my performance improvement actually come from when using in-memory OLTP? So I have here another depiction of the same architecture I showed before, where we have the SQL Server engine, which has the memory optimized tables and indexes, and here we have the engine, the storage engine for memory optimized tables and indexes, and we have a natively compiled stored procedures, query interop, etc. At the top, the connection layer; at the bottom, the memory optimized data file group for a persistent copy of your data. Now, I want to point out the various parts which give you some performance benefits. So the storage engine itself is lock and latch free. And this means you no longer have any lock or latch contention. So if latch contention is a performance bottleneck in your application right now, like it was for the ticket reservation application that we talked about in the foundational session, then just using this storage engine, using memory optimized tables, gives you great benefit. We saw in the demo 7x benefit from that. The second is you have more efficient data access in the storage engine, and in addition, you have native compilation of stored procedures. So this, depending on the kind of work you do, it is generally about 10 to 30 times as efficient as queries or stored procedures against regular disk-based tables. So if you're doing a lot of work in your stored procedures, you can benefit a lot from this gain in efficiency. Then again, if you don't do a lot of work in your stored procedures, if, for example, you manipulate only one row in your stored procedure, then probably most time is being spent in other layers, like, for example, the TDS handler or in the logging, and just speeding up this stack here will not give you a lot of overall benefit. So it really depends on what the procedures look like, how much gain you can actually get there. As for logging, so as I mentioned, we are fully durable, so transactions need to be logged. Now, memory optimized tables require less logging typically than disk-based tables. Main reason is that we don't log any operations on indexes or any inserts, deletes, or any further index maintenance operations. Those do not need to be logged. In addition, our log records are slightly more efficient. But the key point to remember here is that you still have the latency of the log. So your transaction commit of your transaction will not finish until the log record has been hardened to disk. So if you have storage with high latency for the log, then your transactions will still take a long time. Now for the memory optimized data file group, for the persistent copy on disk, for durability purposes, we use sequential I/O here, which is generally more efficient than random I/O, which is typically used for page-based structures. So this is going to be a bit more efficient. But either way, the process to write the rows to this file group runs in the background, so it will not hold up your transactions in any way. One thing also to bear in mind here is that we have not made improvements in the communication stack, TDS handling, the connectivity layer. So things like parameter passing, result set generation, they take the same time for natively compiled stored procedures as they do for traditional interpreted stored procedures. So if you're returning, for example, large result sets from your stored procedure, you may spend a lot of time in result set generation and will not get a lot of overall benefit. So now I want to show or delve a little bit into the performance gains that we saw in the demo itself. So let me just briefly rerun it. So our scenario here was we have an OLTP application, and the application is running slow. Clients are getting slow response times. So we want to figure out what is going on and address these problems. So the simulator runs the workload against the server. And this is against traditional disk-based tables using traditional interpreted T-SQL stored procedures. And we see about 2,400 transactions per second and a lot of latching going on. Right? So then to use in-memory OLTP in this scenario, we migrate a table to in-memory. So for this, I have the script built in, which drops the original disk-based table and creates the new memory optimized table with the same name. So I have the same stored procedures, the same client application, now running the workload against this. So as we can see, we have now about 6-7x performance gain. We went from 2,400 to about 18,000 transactions per second. So now I want to, stopping my workload, I want to quickly go back to the slides. So when we looked at the performance profile of the baseline of the running application, we saw that the main performance bottleneck was the latch contention. And because the in-memory OLTP engine is latch-free, when we migrate the table, just the table, we immediately get this performance gain because, well, we get rid of the latching bottleneck. So then if we go to step 2 of this demo, here I identified, well, I am using the CPU fully, but maybe I can get even more out of it. So I migrated a couple of stored procedures, 2 stored procedures actually, to natively compiled. And running the demo again, so total gain is in this run, it varies a little bit as I mentioned. In this run getting about 20, 23, 22, 23. So there's an additional 3-4 times performance improvement that I'm getting when using these natively compiled stored procedures. So when looking at it, looking at the profile where we have just the in-memory tables, we saw on the performance bottleneck in this case is CPU. I'm using my CPU fully. So how can I use my CPU more efficiently? How can I use the same CPUs to do more work? Well, I migrated the stored procedures to natively compiled, and they use the CPU more efficiently. They require fewer instructions to do exactly the same work. So I get additional gain by doing that. So now I want to mention a couple of characteristics of of applications that are kind of suitable for in-memory OLTP. So first, it needs to be suitable for in-memory processing, right? So you need to have at least enough memory to hold the data in your performance critical tables. And also, if you have any locking or latching issues in your application, also means it's a very good candidate for in-memory OLTP, because, well, we have these latch-free data structures. And then we want the application to be kind of OLTP-like. Well, that sounds a bit vague, but because OLTP covers a very wide range of applications. But some characteristics are like relatively short-lived transactions. We don't deal that well with long-lived transactions because we need to keep all the old data in memory. A high degree of concurrent transactions. That is what in-memory OLTP is really optimized for. So things like stock trading, travel reservation, ticket booking, order processing, these kind of things. And then also there is always a cost associated with the migration. And this cost, and there's a cost-benefit trade-off. The more work you do, the higher the performance gain you can get. So if you migrate just your tables, you will not get as much gain as when you also migrate your stored procedures. And these things become easier if your application, for example, already uses stored procedures. And also, if your performance bottleneck is in a subset of tables and stored procedures, that means you will need to migrate only these tables and stored procedures, and you can leave the rest of your application alone. So now I want to do another short demo. This time I want to show you some actual T-SQL. So this is not as fancy as the other demo application that you saw. The other demo application actually runs 40 threads in parallel and is hitting the system hard and really shows what kind of gain you can get by especially getting rid of the latching in your system. And now I want to show you something more simplistic, single-threaded, and I want to kind of highlight the stored procedures here and also show you a little bit of the syntax and a little bit of the generated files that are going to be on disk. So I have here my database called IMOLTP, and I'm going to create a table here. This is a regular disk-based table. This is just some sample table which has a primary key and a secondary index. And what I'm going to do now is I'm just going to insert 1,000,000 rows in a single transaction. And these are just dummy rows. I just want to show briefly some performance difference. So let me start running this. So if you look at the window on the right-hand side, here is where I want to do my in-memory work in the same database, actually. So what I will need to do first is I will need to enable my database for in-memory by adding a memory-optimized data file group and adding also a container to this file group. And actually these containers are file stream containers. We use file stream technology under the hood. And I have here my table, my memory-optimized table, which looks fairly similar to the disk-based table. So I have the same column names, data types, the same primary key, the same secondary index. But I have here this keyword saying, hey, this is going to be memory optimized. And I'm using here hash indexes, which in CTP1, we support only hash indexes on memory optimized tables. In CTP2, we will also be supporting regular non-clustered indexes. So as we saw, my disk-based script finished, and it took about 32 seconds, right, to insert 1,000,000 rows. So let me go ahead now and enable my my database for in memory and create my table. So what I'm now going to do is I'm going to take the same logic which inserted this 1 million rows, and I'm going to stick it in a natively compiled stored procedure. So we have here some syntax, like you need to say it's with native compilation, a couple of required elements. We have a new element here called an atomic block. What it does, it gives you always gives you a transaction. So when I'm going to run my procedure, at the beginning of the procedure it starts a transaction, at the end it commits if there were no errors. And I have here the exact same T-SQL in there as I was running against my disk-based table. So let me create this stored procedure. So actually what I want to do now is, before I actually execute it, I want to show you a little bit of a flavor of the kind of files we actually have on disk, what we generate. So I have my database ID 7. So we create in the default data directory, we have a folder XTP where we store the generated files. And you see here a number of files. So here we have the DLLs. These are the DLLs for the table and for the stored procedure. And we have another number of generation artifacts. We have, for example, the C file, which was used to compile the DLL, and we have some of our own artifacts related to compilation. And we keep these on disk for supportability purposes. And just to show you that this is actual C. So you can see we have here the typical C constructs. There are defines, type defs, and generally this is all very obfuscated. So you will not be able to do anything with the C code. In fact, you are not required to look at it. We keep it around only for supportability purposes in case there are errors that we need to debug. So we have these files on disk, and also, for example, you cannot tamper with the DLLs because they are loaded in memory. So if I try to delete this DLL, you can see this was not possible because the file is open in SQL Server. Now, the second thing I wanted to show you are the checkpoint files. So we have in my data directory, which is on the D drive, I believe. Yes, we have here the container in my memory optimized data file group. And let me zoom this in a little bit. If you're familiar with FileStream, this may look familiar to you, as we're using FileStream under the hood. So we drill into this folder, and we see here the checkpoint files. So we always pre-create a number of checkpoint files. In this case, we have about 2 gigabytes pre-created. We pre-create one for every core in the system, and I have a 16-core machine here. So these are the files on disk. Normally, you would, as a database administrator or as a user, you would never need to look at these files. These files are all managed for you. So the generated code, like the C code, the DLLs, we generate them when we need them, and we remove them when we don't need them anymore. Similarly with the checkpoint files. So we keep appending them, and when sufficient rows are deleted, we merge them, and we free up the space for you, basically. That is the main thing to keep in mind. We free up the space for you. In the DBA breakout session on Thursday, I will go into a little bit more detail about how this works exactly and what we do with these checkpoint files. Okay, but enough about these files. Get on with the execution already. So let me execute this statement, which inserts this 1 million rows, and now it's finished. So as you can see, this took about 3 seconds compared with 32. So that's about like 11 times as efficient, which is probably what you can expect from pure efficiency gain in stored procedure execution. So remember, we don't have any latching in the system here, so we don't get any benefit from the latch-free data structures, but we do get the benefit from the more efficient execution and more efficient data access. And to show you that we indeed have 1 million rows in there, well, we have 1 million rows on the left-hand side, on the right-hand side, also on the left-hand side. I'm a little bit ahead of myself. I'm already deleting the rows. So now let me also run the delete on the other side. So yeah, as you can see, the delete is also fairly efficient. Delete is especially efficient for memory optimized tables, because all we need to do for deleting a row is just mark the row as deleted. We don't need to update any index structures in place, and we don't need to modify any pages or anything like that. And we have then a garbage collection process which asynchronously cleans up the deleted rows. Okay. So so this was kind of the main content for this session. So we have lots of time for questions and answers. I do want to mention some of the related sessions. So tomorrow we have a session about developer concerns for in-memory OLTP, where I will go into the data structures in a bit more detail about how to create tables, how to access tables, what to do with your regular queries, what to do with your natively compiled stored procedures. And then also a very important point is the transaction semantics, because we have this log-free, concurrency system. So we have, instead of one transaction having to wait behind the log of another transaction, we have that one transaction wins and the other loses, and it will fail, need to be retried. The second related breakout session is about DBA concerns. That is all about memory. Like, how much memory do you need? How much do you need to provision? How do you manage your memory, also in multi-tenant situations, and also storage. So how much storage space do I need? What kind of disks do I need for my data files and for my log files? We also have a hands-on lab. As you can see, there's still a little bit left of the old code name. So the hands-on lab still is titled SQL Server Project Hackathon. So you can try that out at your leisure. I will be at the booth in Server and Cloud Tools this evening, also on Friday. Of course, I'm also available after the sessions, and I will actually also be presenting these two breakout sessions mentioned here. I will be the Ask the Experts as well. So your resources, I guess you've seen this, evaluation. So you can scan this, please evaluate the session. And I will now open it up for Q&A. We have questions. I think I see a question there. The question is, what do the processes look like when I have both disk-based and memory-optimized tables? Is that correct? Yes. Well, the process is just a SQL Server process. All tables live in the same process, in SQL Server.exe. The storage engine for memory-optimized tables is in a DLL, which is linked into the process. So you just have one process. So, well, inside the process, of course, everything is synchronous. So, yeah. Oh, the question is on transaction processing. Yeah, so the transaction processing, when you touch both disk-based and memory-optimized tables in your transaction, is the interaction synchronous or asynchronous? The answer is it is going to be synchronous. So when the transaction commits, at that point, a single log record is written, which functions both for the disk-based tables and for the memory-optimized tables. So it's completely synchronized. Yes. I think I saw a question there. Yeah. Yes, the question is clustered indexes are not supported, correct? Yes, that is correct. Clustered indexes are not supported because no, clustered indexes. The thing is, clustered indexes do not apply to memory optimized tables because we have a different data structure. We have this bunch of rows in memory, which is your table data. Right? This is not an index or anything. This is just your table data, just a bunch of rows. And then you have indexes which contain memory pointers to these rows. So also the indexes don't duplicate data in the rows. And actually, also every index is going to be covering, because you just have the index you just have the memory pointers to the rows directly.
So the non-cluster indexes structures
So
differ in physical point of view if you are talking about a numeric table versus a traditional table.
the question is, do the physical data structures differ between indexes on memory optimized and on disk tables? The answer is yes. They are completely different. The indexes for memory optimized tables don't use pages. They don't duplicate data from the rows. And also we have a novel type of index now available only for memory optimized tables, which are hash indexes, which are completely different from B trees. But the non-clustered indexes on memory optimized tables, which will be coming in CTP2, they are a bit more similar to traditional B trees, but they work a bit differently because they don't have fixed size pages and they are self-maintaining, so you don't need to do any maintenance on these indexes. Yes? The question is there a way to distribute data if your data doesn't fit in memory? Yes, I'm afraid that with this V1 you will, or with SQL 2014, you will need to do it yourself. We hope to do it automatically for you in the future, but you can certainly have like a hot table in memory and a cold table on disk, and just create a union all view of the two, and then it will look like a single table. Yeah, but you will need to take care of the movement between the two tables yourself. Yes. The question is, can TempDB benefit from this new technology? Yes, absolutely. Unfortunately, we are not at the stage yet where we can wholesale put TempDB in memory, because the surface area supported by TempDB is much bigger than can be supported by in-memory OLTP at this point. However, there are some ways you can already leverage it in places where you would now use temp tables, like you can use memory optimized table types. So you can create a table variable based on the memory optimized table type and use this in your regular transactions. That's just going to work. Let's see, question there. The question is, can hackathon tables spool out to the buffer pool or benefit from a buffer pool extension? No. The answer is no. It's a separate space, separate from the buffer pool. So the question is, what knobs do you have to manage memory for memory optimized tables? We will be leveraging a resource governor. We're extending it to be able to associate a database with a resource pool and to have a cap on memory for the resource pool. So you would typically create a resource pool for your database, associate your database with it, and say, hey, you cannot use more than, let's say, 50% of max server memory. It's not at the table level, no. It's at the database level. Also, this feature is coming in CTP2, so CTP1 does not yet have the memory management. Further questions? Yes. The question is, have you compared this technology to switching to SSDs? Well, the demo that I was running, I'm using SSDs for the log and for the data files already for the traditional disk-based. So, yeah. So yeah, we assume that. So this in-memory OLTP is a pure performance scenario. So it is for people who really need the performance and who have worked hard already to optimize their application for performance. So they will definitely already use SSDs for the log, which of course you will need SSDs for the log, otherwise you will not get a high throughput. So yeah, we are assuming you're already using SSDs, basically, for the log at least. Yeah. Further questions? Yes?
The option for memory is at the table level. How about partitions?
The question is, the option for memory is at the table level, as I showed. What about partitions? As of yet, in SQL 14, we will not yet have support at the partition level. So it is only at the table level that you will be able to say this. So if you want to have a partitioning scheme where you have like a partition in memory and some partitions on disk, you will need to do some work manually for the partition management, move them between memory and disk. Yes. Further questions? Yes. Will SQL Server 2012 also benefit from this technology? No, this ships as part of SQL Server 2014. It will not be included in the service pack for 2012. So it's a good reason for you to upgrade. Yes. Is this only available in Enterprise Edition? Yes. Also developer and eval, but it is not going to be in standard. Yes. Well, question is, will SQL Server 2013 benefit from this technology? SharePoint, sorry. Will SharePoint 2013 benefit from in-memory OLTP? I'm afraid not. It's not yet, but we are investigating this. I'm actually getting a lot more questions about this than I had expected. So yeah, we'll definitely look into this a little bit more as we go forward. So if you want to think about this feature in SQL 2014, this is really for apps that kind of hit the ceiling in terms of the performance they can get out of their servers. They use SSD for the log, they added lots of memory, and there's still not enough throughput, right? So you go the extra mile and use this feature. Now with future versions, we will also be looking at other scenarios like ISV scenarios and making adoption a bit easier, and also SharePoint will definitely be one of the targets. Yes? The question is, when do the DLLs get created? The DLLs get first created when you create a table or when you create the stored procedure. So the table creation or stored procedure creation will only finish once the DLL is created and is loaded into memory. Now, when the server crashes or shuts down and restarts, then we actually recreate the DLLs. We don't keep them around because we don't want people to be able to tamper with them. So we recompile the table DLLs during database recovery. And after that, the stored procedure DLLs are recreated at first execution. The question is, there's no way to inject a DLL? No, that's correct. It's completely managed by SQL Server, and they're always recreated, never loaded from disk. Further questions? Yes? What does XTP stand for? It stands for Extreme Transaction Processing, which is what we want to achieve with this feature. Okay. Further questions? Yes. What's the question? Does this technology work with high availability? Yeah, this is not yet in CTP1, but in CTP2, in-memory OLTP will be fully integrated with always-on availability groups. So we will not integrate with mirroring because we're deprecating the feature, but it's integrated with availability groups. Also, failover clustering will be supported as well as log shipping. Further questions? No? Okay, well then I thank you very much. I think we're a bit early, so have a longer break.